about the math will change this year. The math of infinity or the math of infinitesimal. I don't even know how to spell that, but whatever. Infinitesimal is something infinitely small. We're going to start today talking about things that are like infinitely small or infinitely close to something. And that's crucial. 2 problems solved by calculus discovered by Isaac Newton during a pandemic. He was alive during the bubonic plague. He was in college during the bubonic plague. And they told everybody at Cambridge, yo, you got to go home. The bubonic plague is coming. We don't want you all around each other while the bubonic plague is around. He grabbed some books from the Cambridge library, went home, and discovered calculus and much of physics. What did you guys do your freshman year during distance learning? Did you guys accomplish anything big? No? Nothing? Okay, well, Newton accomplished the discovery of major things. Cool. And he discovered how to find the tangent line anywhere on a curve. This is the key thing we're going to learn in semester 1. It's called the derivative. You don't know what that means yet. We'll figure it out in unit 2. And then he discovered how to find the area under an irregular shape, which actually means more than that. And like both of these mean a lot more than just that. But this is what we're going to do in semester 2. And we're going to learn about integrals. Integral calculus, derivative calculus, you don't need to know what that means, but that's what we're learning. So if like your siblings who've taken this class before, or if your friends who've already taken the class, be like, yo, our derivatives. You don't know that yet, but you will, okay? Oh, have you guys gotten an integrals yet? You don't know that yet, but you will. Cool. This isn't in your notes, but you can put this like limit is what we need to figure out before we handle any of that. Limits is the building block of calculus. We're going to learn about limits. Okay, cool. And to help introduce you to limits, we are going to look at different types of functions, like piecewise functions. Now, this says graphing piecewise functions. You're never going to have to graph these. Usually when I tell students, oh yeah, we're graphing piecewise functions, everybody's like, oh, hate it. Hate piecewise functions. Don't worry about graphing piecewise functions. I'll help you with the graphs. You just got to be able to understand what we're getting and using them and getting the right answers, okay? All we're going to start with, and then I'll show you what the graph is, like finding some function value. Now, before we get into that, if I gave you some random function g of x that's not a piecewise function, g of x is 2x plus 3, could you tell me what g of 4 is? Tell your neighbors, what is g of 4 if g of x is 2x plus 3? G is like a machine. If it's using x, you would take your x value, multiply it by 2, and then add 3. If you decide to use 4 in your machine, you would take 2, multiply it by 4, and then add 3. If you said 11, good. I'm just plugging in the value and figuring out what the output is. Cool? That's no big deal, right? All right. The difference with piecewise functions is that we only use certain x's for certain pieces. We will only use the x's less than 2 in the piece x plus 3. We will only use x's bigger than or equal to 2 in the piece negative 2x plus 5. So if I ask you what is f of 1, it's like, okay, I'm using 1 instead of x. You are not plugging in 1 everywhere. No, because you were told when x is less than 1, you should be using this piece. And if I plug 1 into that piece, you get 4. Got that? Cool. Do the other two. What are the other two? What's f of 2? What's f of 3? Tell your neighbors, what do we get for FM2 and FM3? Good. 2 and 3 are both greater than or equal to 2. They are both greater than or equal to this 2, which means we are going to use the bottom piece. I will be plugging 2 into negative 2 times x plus 5. I get negative 4 plus 5, which is 1. I'll keep this in blue. And then if I plug in 3, I'd get negative 6 plus 5, which is negative 1. Cool. Great. Now, let's look at these bottom two. I'm not asking you what we are going to get exactly. I'm asking you what are we going to get close to, okay? So the question is, if you plugged in 1.99999999999, just keep going. You plugged it into your function, your y value is close to what? Tell your neighbors, what do you think the answer to this question is? Like if I plugged in this, I'm going to get a y value close to what number? Tell your neighbors, what do you think we get? Yeah? And then what about 2.00001? Plug that in. What do you think you're going to get a value close to? What do you think, Arceo?
Probably like 3.
Well, is this bigger than or less than 2? Less than 2. This is the thought process we're going through. We are first saying, okay, this is less than 2. Less than 2. That's less than 2. When I'm close to, I don't have the perspective. Since this is less than 2, I'm going to use this piece. Now, if I plugged 2 into this piece, I would get 5. If I plugged in something close to 2 into this piece, I would get something close to 5. Yeah, you're going to get 4.999999, right? Like if you plug in 1.99999 here and add 3, you're going to get 4.999. I'm kind of going about it a different way. I'm saying, oh, this is close to 2. I am plugging this value in to the top piece. If I plug in 2, I get 5. Well, that means if I plug in something very, very close to 2 into this piece, I'd get a value close to 5. Got it? Cool. The other one, same deal. This is close to 2, but it's a little bit bigger than 2. Since it's a little bit bigger than 2, I'm going to be using the blue piece, the bottom piece. And if I plug in 2 into the bottom piece, I already know that I get 1. Well, that means if I plug in something close to 2 into the bottom piece, I'm also going to get a y value close to 1. Now, it's from this kind of experiment and this process that we can kind of create the graph. Now, you don't have to be able to do this, but I'm going to like challenge you a little bit later to see if you can create the graph. We can start saying, okay, I got my red piece, 1, 4. A red dot at 1, 4. If I plugged in 0, I'd get 3. If I plug in, okay, this is my red piece. Now, my red piece is getting close to 2, 5. So as I get closer to 2, I'm going to get closer to 5. If I plugged in 1.999, I'd get 4.999. I'm going to get really, really, really close to 5, infinitely close to 5, but I'll never get there. And this is the idea of having an open circle. It's like we're going to get close to this value, but we're never actually going to get to this 0.25. We'll get to 1.9 repeated and 4.9 repeated. Infinitely close to, but not there. On the other side, though, I'm able to plug in 2 into the blue piece. I get the 0.21, and I am approaching this 0.21, and boom, I just created my graph. If you don't know how to do that, it's actually no big deal. You're fine. We're going to have to either take this and answer some questions, or we're going to have to take a graph already given to us and answer some questions. You're never going to have to graph. Okay? Graphs might help you answer. All right. Boom. Your turn. Can you give me the answer to these 5? This is a little bit different. We have a piece for x is less than 1. We have a piece for x equals 1. And we have a piece for x is greater than 1. Go. Answer and check. Go. What's g of 0? What's g of 1? What's g of 2? What's g of 0.999999 going to be close to? What's g of 1.000000001 going to be close to? That's a 6. I'm really sorry. You are not the first people that asked me that. I appreciate chose. You being brave enough to ask. Because everybody else is thinking it, but you asked. So thank you. Check with your neighbors. Looks like some of us are already done waiting for the next thing. Bored to death by this class. Some of us have different things than our neighbors. We're good on the top. Let's see if we can get the bottom. What are these two, Fisher? What are these two guys? Let's get the bottom 2. Those are the most important ones. Check that one again. Wait, let me see your other one. Nice. Check with Wynn. She's got it.
Really, really close.
Good. We got it. We got it. Good. All right. So, I already noticed some people it's like, oh yeah, I got this. No big deal. Some people, it's taking us a little bit of time, a little bit of thought. That's okay. Okay? If you were at your table, and this is a breeze for you, don't just give people at your table the answers. Don't you dare. That is hurting them, not helping them. Let them struggle and be there to help. Be there to check. Got that? Cool. We got 3 pieces. I'm going to get 3 answers, a red answer, a green answer, or a blue answer. Okay, I like to color coordinate things because it, I don't know, might help some people. 0 is less than 1. If I plug in 0, I plug it into the top, I get 3. 1 equals 1, I get 6. 2 is greater than 1. Greater than 1, I plug into that, I get 6. I don't like how I get 2 different 6s. I mean, I don't like how we get 6 twice, but notice how they're 2 different 6s. We got a green 6 when x is 1, and we got this blue 6 when x is bigger than 1. Now, 0.9999 is less than 1. Cool. Red piece. I'm going to get a red answer. If I plugged 1 into the red piece, I would get 2. If I plug in something close to 1 into the red piece, I'd get something close to 2. Got it? If I plugged in something bigger than 1, like 1.0001, I'd be using the blue piece. If I plug 1 into the blue piece, I'd get 5. If I plugged in something close to 1 into the blue piece, I'd get something close to 5. Got it? The key to that is like we're close to 5. We don't equal 5. We're close to. We're approaching 5. We're approaching 2. Now, if I asked you to graph, this is what I'd probably expect you to do. You got the red piece. That's got the point 0.03. It is going to approach the location 1, 2, but it'll never get to 1, 2. So we're going to go through 3, and we're going to get close to 1, 2, but we'll never get there. We're approaching the location of y equals 1. At 1, we have the y coordinate 6. Boom. I have 1 green dot. Then the blue piece has the point 2,6, so same location, but the blue piece is going to get close to 1,5. So it will get close to this point here at 1.5. It'll never get there. We'll get to 1.0001 and 5.0001. We're getting close to the 0.15. We'll never get there. Boom, we create this graph. Great. If you don't understand how to create that, that's fine. But like, that's what it is. Here's another one. Now, I don't want to call this a piecewise function because it's really going to be dominated by x squared. We're going to use x squared for every single x except for one x, -2. But at -2, we are going to have the point 1. I'm going to call this a pointwise function. It might not be the correct terminology, but whatever. These are my notes. I can do whatever I want. We're calling this a pointwise function. Answer these 5 questions. What's h of -3, h of 4, h of -2? Then answer h of -2.0001. What is that close to? H of -1.999. What is that going to be close to? And then the question is, what does the graph look like? See if you can figure that out. What's up? Yeah. Good. Nice, Noble. If everybody's with Noble, everybody's on the right track, crushing it. All right, Oaks. Wait, what is that? Nice. Yes. Thought it was a 4. Very nice, Septula. If everybody's with Septula, you guys are all on the right track. Try again, Anderson. Make sure you're checking with my boy Shav. Stock, you're already there. Good. So what's the graph look like? That's the next challenge. Good. Good. Very good. Yo, I get a red 9, a red 16, and I get a green 1. At -2, I'm supposed to use 1. If it's not -2, I square it. Well, if I plug in -2 into x squared, I get +4. If I plug in something close to -2 into x squared, I'm going to get something close to 4. If I plug in something close to -2 into x squared, I'm going to get something close to 4. Now, what does the graph look like? Well, it looks like x squared. With one exception. I'm not supposed to have a point on x squared at -2. I'm not supposed to have this point. What is this point? Oh, that point is -2, 4. Now I get really close to -2, 4, but I never get there because I'm not allowed to plug -2 into x squared. -2 squared 4. I'm doing the really close to, Sahota. The really close to. I'm doing the really close to. Now, you are right. In this function h, if I plugged in -2, I should be just getting 1, which means I need that green point, -2, 1. This is what this graph of this pointwise function looks like. Every single x value, you're using x squared, except not at -2. I don't plug it in. I'm going to get really close to it. I'm going to have -2.0001, 4.0001. I'm going to have -1.99999, 3.9999. I'm going to get really close to it, but I'll never actually get here. And then I have this other point. We will continue after lunch. we go. Next function, let's go for it. Start by plugging in 1. We're going to work through this together. Start by plugging in 1 into this one. Go. Plug in 1. What do you get? On the next one. There's not a piecewise. This is not a pointwise. This is just J. It has an expression. You guys think of an equation. This is just J. Plug in 1. What do you get? Plug in 1. What do you get? Nice. We get 3. Cool. Plug in 3. These are my notes. I get to do whatever I want with them. So I'm adding a question. Please find J of 3. Please find J of 3. What's J of 3? I'm adding this to my notes. They are my notes. I can do whatever I want to them. Pause. You're making it hard. Plug in 3. What do we get? 5. Good. 5. Great. Now, plug in 1.5. Well, I don't want to. Because I don't want to take 1.5 and multiply by 1.5 and then subtract 4 and divide it by a half. I don't want to do that. Negative a half. Okay? Could I potentially do something, some of you have already done this, to J, where I make it look different, and maybe it'll be something where 1.5 is easier to plug into. Tell your neighbors, what is something you do so that J looks different, and you can easily plug in 1.6? Yeah, that's right. All right, ready? Many of you are a little off. You guys remember that this is a difference of squares, and you could write this as x plus 2 times x minus 2. Okay, so if I plugged in 1.5, I would want to plug it in here because it's going to be easy to work with. Let's see what that looks like. 1.5 plus 2 is 3.5. 1.5 minus 2 is negative 0.5. And then 1.5 minus 2 is negative 0.5. What do you get when you do that? 3.5. Great. Because these cancel. You get 3.5. Okay, do 2.5. Using the simplified x plus 2, x minus 2 over x minus 2, plug in 2.5, what do you get? $4.5 times 0.5 divided by 0.5. So the 0.5 cancel, and you get 4.5. Skip J of 2, we'll come back to it. Upstairs. Did you already finish your test? Oh, nice. Okay, yeah, put it there. Join us for the lesson. Does both of the tests there, or is your test still upstairs? Respect. Thanks. Come on and join us. Leave your phones over there. Do the bottom 2. Do the bottom 2. Do the bottom 2. Leave your backpacks over there. Oh, leave your phones over there. Good. Do the bottom 2. What do you get? Okay, for the bottom 2, I'm thinking about plugging in 2. Now, I'm going to kind of go through the process here where it's like, well, the x minus 2s and the x minus 2s just kind of went away. So it's like, if I plug in 2, I probably could just plug it into x plus 2. And if I plug in something close to 2, I'm going to get something close to 2 plus 2, which is 4. You put 4 and 4, you're right. You nailed it. Okay? But the way it looks like is kind of a little bit deceiving. We should get like 3.9999 times negative 0.0001 divided by negative 0.00001. Okay? Do we see how that looks? And why we get 4 is because these negative small numbers, they're very, very close to 0, but they're not exactly 0. They cancel. Okay? And it'll be the same thing. Now the question is, what is J of 2? What is J of 2? Tell your neighbors, what do you think J of 2 is? What is J of 2? J of 2 is confusing, right? A lot of us are like, I don't know, is it 0? Is it 1? Is it negative 1? Is it 4? Is it? The problem with J of 2 is if you plugged it into the original equation just like you see it, you get 0 over 0. And 0 over 0 is confusing because you've been told in the past that when you divide any number into 0, you get 0. When you divide by 0, you get undefined. You've been told that a number divided by a number is 1. So what the heck is 0 over 0? Like, which one of these wins? Well, it turns out this one wins. You're not allowed to divide by 0, including by itself. So this is undefined. If you got that right, great. If you didn't get it right, who cares? All you need to know from now on is 0 divided by 0 is not a number. However, it is an indication of something. It is an indication that there's a hole, okay? Because it's like we could cancel the zeros. The problem is you don't know what's next to the 0 if you plug it in here. Look down here. If you thought about plugging in 2 into this guy, okay. You'd get 4 times 0 over 0. If I plug 2 into this guy, you get 4 times 0 over 0. Now that's still 0 over 0, that's still undefined, but you could think about what would happen if those zeros would cancel. You'd have 4. What ends up happening is that this 4 shows up when we plug in values close to 2, because we're not dividing by 0, we're dividing by something close to 0, but it still has value. But when we divide by 0 on the dot, that's not allowed. What happens is that this graph, J, looks just like the graph x plus 2. It is a simple line with one exception. You're not allowed to plug 2 into it, so you don't have a point. But we know that point's location is really close to 4. Sweet. Okay. Last one, then we got to move on. So try this one out for size. And then try to draw the graph as a challenge. Good. We know what absolute value is, right? This is a fun one. What are we getting? Let me see. Good. Nice. See if you can do the graph. See if you can do the graph. See if you can do the graph. Nice tool. Right idea, but wrong execution. This is a Y value, that's a Y value. Those Y values are consistently -1. You get these Y values to the left of 0. You get, oh, check this one again. You get these Y values to the right of 0. What's your graph look like? You'll figure it out. Don't remember. Try to just figure it out. What's the graph look like? You guys figure it out?
I don't know. Is it really graph?
Nice. Rockmiller. You familiar with this one, or is this new to you? Very good, bud. All right. We see that you're going to get -1 when you're plugging in a negative value. Any negative value, you get the Y value -1. So here's a -1, here's a -1, here's a -1, and all the values are -1. Even really, really close to 0, we would get a number divided by itself. So it's not 0 over 0. We get something divided by itself. So we would get -1 even if we plug in -0.00001. Because I'd get positive 0.00001 divided by negative 0.00001. Yes, it's close to 0 over 0, but it is a number divided by itself. So that's -1. So that means up to 0.0001 negative 0.0001, I'm going to have a value of -1. So I'm approaching this location 0, -1. Then, to the right of 0, I get 1, including a little bit to the right of 0. All of these values are +1. So I got a +1 here, a +1 here, a +1. I got all these +1s, including at 0.001, I got a +1. Now, I am not allowed to plug in 0. Mr. Messner told me that 0 over 0 is bad and it's undefined, and he is right. Good. So that is why you don't see any points anywhere, but you do have an open circle at +1 because the piece on the right of 0 is approaching that. Piece on the left of 0, all -1. Cool. All right, now let's get into a limit. If we understand that, Creole, we understand limit. Yep. No, because it would keep going on forever and ever and ever, either a +1 or -1. Okay, here we go. Limits are all about the approaches, not about the equals. Limits are about approaches. Now, the questions we will ultimately get to is find a limit as x approaches a certain number. I'm going to pick a number just as an example. I'm going to say 4. Okay? 4. Now, your answer is potentially a y value that we are approaching. But to be able to answer this question, what is our function doing as x is getting close to 4? You need to do the following. You need to look to the left of 4. This is an undercase LIM. It stands for the limit. This is an undercase LIM. And this is x arrow 4 with a minus sign in the exponent. If you want to answer this question, you need to first check this. Now, what this means is you are checking to the left of 4. The negative symbol means left. To the left of 4 means you're using a value like 3.999 as x. You were just using values like 3.9999 earlier on those functions that we were analyzing. So this is not like new to you. This is called the left hand limit for short. Cool. So again, if you were trying to answer this question, you will first check this. Cool? You will find that left-hand limit. But you're not done yet. After you've checked the left-hand limit, you need to go ahead and check the right-hand limit. Or you need to check the limit as x approaches 4. The plus means from the right. This is from the right. Or use a value just bigger than 4. Again, we're talking about close to, not equals to. So what are we approaching? What are we getting close to? This is called the right-hand limit. So again, if they ask you, what is this limit? You first check the left-hand limit. You then check the right-hand limit. If these limits equal each other, let's say this limit was 3 and this limit was 3, then your answer to this question is 3. If your left-hand limit equals your right-hand limit, that equals your, what we'll call, general limit. We'll call this the general limit. Let's say we have the same question. I asked you, hey guys, what's the limit as x approaches 4? Well, if your left-hand limit was 3, but your right-hand limit was 5, your left-hand limit and your right-hand limit are not the same. We say the limit in general does not exist. If your left-hand limit does not equal your right-hand limit, I keep doing that. If your left-hand limit does not equal your right-hand limit, then the general limit does not exist. We are going to repeat the same function. Okay? But I'm going to give you the graph. And the questions I'm going to ask are now limit questions. Nailed it. Doesn't have to be perfect, Arno. Better to just like go with it. We'll watch videos if we don't understand. Okay. Now, on your homework, you will either be given this or you'll be given this. Never both. Okay? So I'm going to give you both right now just to show you two different ways to arrive at the same answers. Cool? And I'm going to start on the bottom row of questions, limit questions. Now, here's our key. I want us to think about this differently than how it is arranged. Go straight to this question. The limit as x approaches 0. If I ask you that question, guys, you do not provide an answer right away. If I ask you this question, what you do is you go back and you check the left-hand limit around 0, and you check your right-hand limit around 0. After answering these two questions, then you can answer that question. Okay? Okay. Now, how do we answer these questions? Well, we do what we were doing earlier. We think about, if I plug in something close to 0, but a little bit less than 0, if I plug in negative 0.00001, what do I get, or what is the y value we are approaching? Okay, now you can do that using the piecewise function given to us, or you can figure that out by using the graph. So I didn't give you enough information about the graph. So let's use our piecewise function, and then we'll fill in. If you plug in negative 0.00001, what do you get? Tell your neighbors. What do you get if you plug in negative 0.001 into your function? Which piece do you use? What do you get? What is the answer? Nailed it. Way to go, Kyle. If I plugged in negative 0.0001, that is a value less than 2. If I'm plugging in 0 into the top piece, I get 3. If I plug in something close to 0 in the top piece, I get 3. Got it? Okay. Again, I'm trying to answer this question. And to answer this question, I have to do this, and then I'm going to do this. Okay, now, same thing. 0 plus. That means 0 to the right. That means you are using and you're thinking about using 0.00001. Okay, go. Do it. Tell your neighbors. Nailed it. 0.001 is still less than 2. Since it's still less than 2, I'm still using the top piece. If I plug in 0 into the top piece, I get 3. If I plug in something very close to 0, a little bit bigger than 0 into the top piece, I still get 3. Now, to answer this question, the original question, all I have to do is look at this number and this number. If they are the same, now I can answer this question and say the answer is the number 3. If these two numbers were different, the answer to this question is does not exist. Got it? It starts with this question. To answer this question, we do the left hand and the right hand limit. We look at our answers to that question, and then boom. That determines whether we get a number or does not exist. Now, what is f of 0? I don't care. It has nothing to do with the limit question. F of 0 is what is happening exactly at 0. Well, it just so happens exactly at 0 I get 3. But honestly, this is a different question, so I'm going to use a different color because it's not related to those red 3s. Okay. Now, let's look at the limit as x approaches 2. We want to answer this question, but to do that, we must look at the left-hand limit and then the right-hand limit. Go. You already did it. Fantastic. You guys are pros. You could do it either using the function or you could do it using the graph. I'm going to show you how to get the answer to this using the graph because we have enough stuff in the graph. Nailed it. Good. Correct? Correct. Now, to answer this question, you look at these two numbers. Nailed it. All over it. Okay. 1.99999. Plugged into there, boom, 5. 2.00001. Which piece do I use? Yep. Fix that answer. Yep.
On my way here.
Okay.
It's just,
Is this number the same as that number? And what's that? Nailed it. Okay. Now, the answers are 5, 1, does not exist, and 1. Okay. But watch how I'm going to get those answers without looking at the equation. We need to be prepared to get these answers by looking at the graph. Okay? So see if you can get the same answers without looking at the equations, without looking at the expression. Ready? Ready? Stay with me. To the left of 2. Okay, I'm thinking 1.9999. I will locate 1.999. Okay, that's 1.999 is to the left of 2. I'm looking to the left of 2 and I notice here is the graph that we are using to the left of 2. As I get closer and closer and closer to 2, I'm getting closer and closer to the y-coordinate of 5. This is how we can get the answer 5 without the equations given to us, which is we're in charge of doing. Like the first couple pages of your homework, it's all graphs. To the right of 2. Okay, to the right of 2, I'm using 2.0001. Okay, I'm going to locate 2.001. 2.001 is right here, to the right of 2. I notice that I'm using this graph to the right of 2. As I get closer and closer to 2, to the right of 2, I'm getting closer and closer to a y coordinate of 1. So that's why that's 1 using the graph. Cool? To answer this question, you look at this answer and this answer. If they are not the same, this does not exist. I do not care that f of 2 happens to equal 1. That is a whole different question that's looking exactly at 2. We're looking about approaching 2 with the limit. Next, do all 8 of these questions go? You can use the graph or you can use the equations, but like try to figure out both. Try to use the graphs if you haven't figured out the graphs yet. Nailed it. Nice, Carlotti. Second time around, it's a lot easier, right?
Yeah.
Yep.
I know we did all this stuff the first day. Now I actually understand it.
There we go. That's all it takes. Sometimes it just takes the second time around.
No, it's still like 0.9. Yeah, so.
All good. Different ways to do it. Anyway, how'd you do? You pick up on this stuff?
No, I'm not gonna lie.
Is Newell helping you?
Yeah, we're figuring like.
Come on. You should be done. Come on. Don't distract. Why is your phone over here? Get your phone out of here. Over there. That's right across. Go.
Oh. Okay. Sorry.
Earl's got it. Earl showed up late, and Earl's got it. Come on, go, go. Nice. Okay. To answer this question, we look at this number and this number. Okay, ready? Here we go. Some of you are like, oh, this class is almost over. I don't have to do anything. Gotta put the time in now. Ready? To answer these questions, these are the questions I should ask first. They should go on the left. To answer these questions, you must first look to the left and to the right. If I look to the left of 2 and to the right of 2, I am going to be using the bottom piece. The left and right of 2 uses x plus 4. If I plug in something a little bit less than 2 into x plus 4, well, if I plug 2 into x plus 4, I get 6. Something a little bit less than 2 plus 4 is going to be something close to 6. Something a little bit bigger than 2 plugged into x plus 4 is going to be 6. Since this number and this number are the same, you get 6. I don't care about the function value. .999. I'm going to go to the graph. 0.999 is to the left, using this piece. As I get closer to 1, these y values are getting closer to 2 because I'm using this top piece. If I plug in 1 into the top piece, I get 2. If I plug in something a little bit less than 1, it's still going to be close to 2. If I plug in 1.001, it's plugging into the blue piece. If I plug in 1 into the blue piece, I get 5. If I plug in something really, really close to 1 in the blue piece, I get 5. Since this is 2 and this is 5, your answer to this is always does not exist. Now, it happens that we have a point, 1, 6. Cool, don't care. That 6 is that point. It's unrelated to that point 6. That's it. Let's try another one. Go. And you know what? I'm going to go ahead and do the bottom row for you. If I plug in 3 and things close to 3, I get 9, 9, 9 all the way across. What are your answers here? That's your answer. You missed a little bit, so you're a little bit off. The key is we're plugging in values into the right piece. If you're to the left of -2, you got -2.0001. That is a value that's not equal to -2. So I would plug it into that piece. If I plug it into that piece, what is the value I'm going to get close to? Okay, ready? To answer this question, all I care about is this question and this question. Okay? If I can figure out these two questions, I'll figure out this question. Okay. To the left of -2. To the left of -2 is a value that's a little bit less than -2. I will be using x squared because it's not a value that's equal to -2. It's close to. So if I plugged in -2 into this x squared, I get 4, which means if I plug in something close to -2, I get something close to 4. Again, this equals to is like misleading. You should be thinking about getting close to, just like we did earlier. Same thing if I use -1.9999. It's not equal to -2, so I'm using the top piece. And I would get the same value. Plug in -1.999 and square it, it's going to be close to 4. Since this is 4 and this is 4, this is 4. Even though the function value is elsewhere, it's 1. Okay? The next question. Tell your neighbors, what was J of 2? Go. What happens when you plugged in 2 into J? What did you get? When you plugged in 2, you got 0 over 0. 0 over 0 is undefined. Yeah, I just made the graph. Just put it up there. To answer this question, what do you have to do? I didn't put it down. You have to do it. Difference in squares. Now, ready? The graph is going to help you. To answer this question, you need to look to the left of 2. You need to look to the right of 2. Now, the graph is going to help you, but the key is being able to get these answers without the graph, and I'll show you that in a second. If I look to the left of 2, what are my y values close to? 4. If you look to the right of 2, what are your y values close to? 4. That means this answer is 4. Now, how do I get that answer without a graph? Because that's what's going to be the challenging question on your homework. Well, you think about, yes, the value is undefined, but the indication of a whole is this 0 over 0. Everybody, write down that 0 over 0 means whole. I'm losing Shotty. Shotty, you good? All right. Whole. Now, we approach locations of whole. So 0 over 0 is an indication that there's going to be a limit. We'll confirm that in a second. To find that location, this is when we factor and we essentially cancel the zeros out, create something that we can plug 2 into to get 4. That's how you're going to get the answer 4 to the left and to the right, is by factoring. Okay? We're skipping the last one. We got to move on. Flip over. What did we learn? Ready? Reviewing what we just did. First things first. Boring locations where there's nothing crazy going on, like at 0. The limit, the function value, they all agreed with each other. Boring. Okay? But most functions, limits, function values will agree with each other. If we're talking about a location where there's nothing going on, the answer is easy. This is the point, and we're approaching that point. Cool? Let's get to the interesting stuff. We jumped. The left-hand limit and the right-hand limit, not the same. Limit didn't exist. I lost you. We jumped. The left-hand limit and the right-hand limit were not the same. The limit did not exist. I'm on the wrong spot. Boom. Limit did not exist. On the jump, the limit did not exist. The hole. Here was a hole. Did we have a limit? Yes. Was it equal to the location of the hole? Yes. Did the point make any difference to the limit? No. We had a hole. We didn't have a point. Did we have a limit? Yes. Jumps? Limit doesn't exist. The left-hand limit will not be equal to the right-hand limit at 2. You're in charge of finding the left-hand limit and the right-hand limit. Speed, Lockmiller. Holes have limits. Because the left-hand limit will approach the right-hand limit's value. In this case, the left and the right are approaching this y-coordinate of, I don't know, we'll call it 2. The y location of the hole is where we're approaching. Holes have limits. Now, we were able to plug in a bunch of different values and we were able to check our answers. We're going to skip over this because it's actually not important for your homework or for your quiz or anything. And I'm just going to give you a big graph. Giving you a big graph. Just the graph, no equation. Could you answer all these questions at the 3 interesting locations? There are lots of uninteresting locations, like at, I don't know, -2. If I asked about -2, your answers would be like 4 all the way around. But I'm going to ask you about the location x equals -4, the location x equals 1, and the location x equals 6. Ready, set, go. I'll do the first one for you. If I plugged in -4.0001, that's right here to the left of -4. I'm using this graph to the left of -4. As I get closer to -4, I'm getting closer to the y-coordinate of 2. That's my answer to the first one, 2. Keep going. The limits are all about close to's. The function value is what is going on at that point. Do you see a point above x equals -2? No. F of -4 is undefined. But to the right, to the left of -4, I'm approaching that hole's location of 2. Holes have limits. They may or may not have function value. What about 1? What about 6? Holes have limits. We are approaching the location of the hole to the left and to the right. We're close to that value of the hole. This is 4. This is -2. This does not exist. This happens to be 4. This is like plugging in less than or equal to in our piecewise function. This is 5. This is 5, meaning this is 5, even though the function value is 2. Hold on. You will need to be able to interpret tables and pick the right table that expresses the statement. As x gets closer to 9, my y's will get closer to 5. Just make sure you understand x's versus y. Now, things may seem tricky when you don't have graphs. But remember, most graphs are easy. There's no crazy jumps holes to worry about in most graphs, which means limits are usually just going to be equal to what you get when you plug in the value or the function value. If I plug in 2, I get 12. The limit's going to be 12. If I plugged in 1.999 and cube it and add 2 times that, it's going to be something close to 12. If I plug in 2 pi over 3, I'm going to get the sine of 2 pi over 3, which is root 3 over 2. That's the limit. I don't have anything crazy going on. If I plug in 2, I get e squared. That's the limit. It's equal to the function value. Hold on. But if I plug in a value and I get 0 over 0, that is an indication of a hole. Holes have limits. You will need to factor to be able to discover the hole's location. You will work on that on your homework. See you guys on Thursday. Thank you. All right. We got to discover the location of this hole because holes have limits. I factor the bottom. The bottom is the difference of squares. You can cancel the x minus 4. That's like canceling the zeros when I plug in 4. If I plugged in 4, I'd get 0 over 0 times 8. Well, 0 over 0 times 8 technically is undefined, but imagine that you cancel the zeros. What would you get? 1/8. Same goes here. If I plug in 0, I get 0 over 0. That is an indication of a hole. This is like when we first looked through this guy, okay? This guy. When we first introduced this guy, we realized we could plug in like 1.999 and 2.001. We could plug in those values. We would get 4. But at 2, we can't, and we wouldn't get anything. So this is the location of a hole. Holes have limits, because the left and the right will equal the same thing. To find the location of said hole, you have to factor to kind of eliminate the 0 over 0. To factor this, I get x squared 2 plus x cubed. Factoring at a greatest common factor, I get x squared 6x cubed minus 3. If I plugged in 0, I'd get 0 times 2 over 0 times negative 3. Imagine those zeros cancel. They don't, but like if they did, or if you thought about plugging in values close to 0, like having values that ended up being close to 0, like 0.001, 0.0001, these do cancel, then we get our answer negative 2/3. Okay? The rest are just like, are you sure you get it? Here, I'm just giving you the equation. Here, I'm just giving you the graph. Like, you have to be ready to either have the equation of just a function, a piecewise function, or a graph. If I'm asked to find this, I must check this and this. If I check this, I'm thinking about plugging 1.999 in, plugging in 1.999 in here. Plugging in 2, I get 1. If I plug in something close to 2, I get something close to 1. 2 to the right, 2.001, I'd use this. If I plug 2 into this, I'd get negative 2. If I plug in something close to 2 into this, I'd get something close to negative 2. Same here, we're asking about 4. So you gotta look to the left of 4, you gotta look to the right of 4. To the left of 4, 3.9999. Use the bottom piece. If I plug in 4 into the bottom piece, I'd get 0. If I plug in something close to 4 in the bottom piece, I'd get something close to 0. If I plug in 4.001, I'd use the top piece. If I plug in 4 into the top piece, I get 0. If I plug in something to 4, close to 4 in the top piece, I get 0. Since the left and the right are the same, that limit is 0. All right, that's good. Peace.